Hello everybody, how's it going today? My name is Connor, welcome back to another video. In this one we're going to be talking about my latest new project. It is a logic simulator that runs asynchronously on a asynchronous runtime, in this case Tokyo. It is also a scripting language, or I guess you could call it a scripting language. It is a kind of a declarative language that lets you, I don't know if that's the right term, but that lets you kind of set up these circuits with logic gates, and then you can then interpret them and run them in a interface that allows you to set the bits high or low, or set the signals high or low, and 1 or 0, etc. So this project is a lot more condensed than my previous projects. The last few projects were really a lot of code. This one has remained pretty simple. I've mostly just been tweaking things for the past week, and then the main concept has mostly stayed the same. So what do I mean by a logic simulator? Well, I don't know if you know this, but all computers inside, let's see here, those are all my browser tabs. All computers on the inside are made up of these electronic constructs known as logic gates. So logic gates, they have these symbols in the schematics. There are only a few of them, and most of them are derivatives of each other. So there's only a few basic ones, but these are really all you need in order to get a a fully functional computer like the one you're watching this video on up and running. So how they work is they take usually 2 inputs. You can also make variants taking more inputs and do like kind of composite operations. But usually they take 1 or 2 inputs, and they perform some kind of binary operation on them. So they basically compare the 2 values in some kind of way, and then depending on what 2 binary values, 1 or 0, high or low, that they receive, they output another binary value. So, and they can be represented by something called a truth table. I'm sure it's on this Wikipedia page somewhere. Yeah, here we go. So here's some truth tables. What you have here is a representation of what happens when you input values, and what happens like what output do you get when you input something. So for the buffer, for example, which this is mostly just a pass-through, actually it is just a pass-through. All it does is just outputs the same value that was input into it. So I actually call this an identity operation. I didn't know there was actually a name for it, but I guess it makes sense, since usually logic gates and transistors and operations in general tend to have a bit of delay between when they receive their input and when they output their stuff. So, and that's actually kind of an important property that we'll get into in a sec. Now, I didn't realize what's going on actually until I started this project, so I'm learning stuff. So NOT gate, or an inverter, will output the opposite of what the input is. So you can see that you have if you input a 0, it'll output a 1. If you input a 1, it'll output a 0. So and you'll notice that the symbol here has a little bubble, and what it's talking about here in the article is that indicates that the output of that gate is inverted. So a NOT gate is just an inverted version of a buffer, which is an identity operation. It outputs the same thing that it gets as input, except a NOT, that's inverted, so it outputs the opposite of what it gets as input. So going into the what I call the binary gates, because they, these are unary gates because they take 1 input. These are binary gates because they take 2 inputs. This is kind of what I've gone to calling them. I don't know if that's a popular term, probably not, but it's whatever. So you have an AND gate, which is basically it's saying the expression this and this need to be high, right? And this need to be 1. A and B both need to be 1, and then the output is 1. So the output is only 1 if A and B are both 1, as you can see in the truth table over here. You have the OR gate, which is A or B need to be 1 in order for it to be 1. So it's only 1 if both are 0. Oh, sorry, it's only 0 if both are 0. It's 1 otherwise. One that would be, it's only 1 if both are 0 is I believe the NOR gate, yeah. There's the opposite of NOR gate, we'll get into that in a sec. NAND gate is an inverted version of the AND gate. Notice by inverted, I mean the output is inverted. So if A and B are both 1, the output will be 0, otherwise it'll be 1, right? So, and that's what you can see in the truth table here. And then the NOR gate is again an inverted OR gate. So it'll only be 1 if output is 0. And then you have the XOR gate. And the XOR gate is kind of interesting. What you have here is if only A or only B are 1, then it will output 1. If they're both 0 or if they're both 1, then it outputs 0. This is basically kind of checking for equality between the 2 bits. Or, sorry, inequality between the 2 bits. The XNOR gate would be the opposite. It checks for equality between the 2 bits, right? So, anyway. So, yeah, that's just the truth tables. That's just what it all is. Going back to my code, all these logic gates are built up of signals and transistors, and they can all be made out of transistors. Transistors and resistors in a real life scenario, but you know, what is what it is. No capacitors involved. Nothing like that involved, unless you want to get it super fancy. Literally just you plug them in the transistors, and what you get is what you get. So, going back to my project, I'm going to give you a little rundown of the scripting language. It's going to be kind of more a demonstrational video, just so you know what's going on, right? So, now we'll get into the deep dive of the code probably in the next video or two. This is the language that I've developed. It's still a work in progress. I don't even have syntax highlighting for it in VS Code yet. Not like my assembly language I made a plugin for. But let's see here. So how this works is the main is the one that's actually executed in the emulator, in the simulator, and you have the name of each one of these is kind of, you can think of them like a function, but it's really more like a circuit. So how the format goes is you have the name of the circuit, then in brackets you have its inputs, then you have a right arrow, or it's really just, you know, combination of this symbol and this symbol, but I have a fancy font that turns into that. You have a dash open caret, or sorry, close caret, dash greater than, and then you have the outputs listed, and there's no commas or anything, just spaces. And then in the braces, you have a list of connections, right? So these are not assignments, these are connections. And all this runs in parallel. That's the important thing to remember about working with hardware design, is that in a language like Rust, where everything happens sequentially, this doesn't apply here. So and what these assignments are is or connections. I call them assignments. They're really just connections. And what these are is you can connect the left-hand side as output and the right-hand side as input. So, for example, here I have another circuit actually that I'm referencing inside of this circuit. It has the capability to do that, and it will connect it all up the circuitry in here inside, and it'll basically replace this with all of this circuitry up here. So, and then up in here, you see you have multiple assignments or multiple connections going on. So, and then you can even make temporary connections. So if it's like this S connection is not part of the inputs or the outputs, it's just a temporary kind of alias, I guess you could say. Just like the circuits themselves are aliases for these connections, right? So just a more succinct way to represent things. So here what we have is a JK flip-flop. I can actually show you what this looks like. Sorry, I haven't even done that yet. I was going to do that at the start of the video, but I got nerdy with it. So let's do a quick little demonstration of what this actually looks like. A JK flip-flop circuit is, I'll get into it in a sec, but I'll just show it right here. So you see we have the inputs, we have our J and K inputs, and we can set them high or low. And then we have our outputs. So this is a clock. This is always active. This is just it's alternating every 1 second. It's kind of like a clock signal, like a crystal clock in actual electronics. But I have this one set very slow so it doesn't hurt your eyes by flashing a bunch. And I have the Q and the Q inverted outputs. So what that actually looks like in logic is JK flip-flop. Mine's actually using a NAND gates, so I'm not going to do the NOR gate, but this is what JK flip-flop looks like with NAND gates. Let's zoom in on that actually, so you can see on mobile. Oh, they actually have a mobile site that okay, that's pretty cool. So yeah, this is what the JK flip-flop looks like. Remember this, these are the symbols for NAND gates, which is the inverted AND gate. These are actually 3 input NAND gates over here, which is just this and this and this, right? It's like stacking two AND gates together and then putting an inverter on AND, because it's a NAND gate, 3 input NAND gate. So it will only output 1 if all 3 of these, or sorry, no, it will output 1 unless all 3 of these are 0. It will only output 0 if all of these are 1. So, and then what we do have here, notice we have some cross-coupling here going on with these other NAND gates, these 2 input NAND gates. So, you don't need to understand what that actually means right now. All it means is just it's a feedback loop. So, and this takes advantage of the fact that there's a bit of delay in these digital circuits, in these digital gates. So what will actually happen is actually, let's see if we can JK flip-flop, animation. Let's see here. See if this has a good animation. Okay. Okay, yeah, whatever. Yeah, I don't care. Let's see here. I think I've been to this website before. This is the thing I was just on. All right, let's see. Load. Okay, whatever. I can't find a good animation for it, but essentially what happens is where was it? Sorry, I'm like kind of a mess today. All right, so let's go over here. What happens is the J input is to set the Q input high, I think, right? Is that how it works? Yeah, J sets Q high, and K will set Q inverted high. And that's what this means, is it's Q inverted. I can't type the bar symbol in my my code editor, so I just, you know. So anyway, and then what that does is it will basically, when you set the J input high and the clock is high, it will take, so like the J takes as input the output of Q bar, or sorry, the Q inverted, right? So if this is high and all three are high, then this will go and it'll kind of send the signal into this NAND gate, which this is also high, because it's the same signal, right, as the Q inverted. And so this will be set high, so the Q will be set high, which means that is that right? Like that. Anyway, it doesn't matter that much. All you need to know is that it just toggles these two things whenever the clock edge goes high. And so like whenever the yeah, no, okay, yeah, so I do actually have it backwards in the code, but either way, it's a circuit that's going on inside of code. It's being simulated. I can go over real quick what it actually does under the hood. So what I mean by being asynchronous is every one of these little logic gates, every one of these connections is its own independent asynchronous task. And if you're familiar with asynchronous programming, you'll know what I'm talking about. But if not, then essentially what's going on is we have a number of things happening in parallel, so, or at least happening concurrently. So and actually in this circuit, in the simulation logic, it's actually only happening on one thread right now. So you can see that where am I using this at? Yeah, so I'm building a Tokyo runtime inside of this simulator, and it's actually see, I got the worker threads commented out right now. It's using the current thread runtime, so it's only working on one thread right now. And then yeah, I just spawn a thread manually and run it on that thread. So what that means is that it's rapidly switching between all of these different simulations at like a rate of like, you know, thousands of times a second at least. So what that does is it allows each circuit to be dependent only on its own individual inputs and outputs. And that's important for digital logic, I feel like. Or at least simulation of digital logic, because that's how it works in real life, right? You know, components don't care where you hook up to them. They just know, they just care about themselves. They just care about, you know, what they see in their little local space of, you know, what are my inputs? Okay, these are my inputs. I'm going to give you my output. Do whatever you want with it, you know? I wanted to kind of try to simulate that in code. So that's what I'm doing. So we can see that we have a few different modules here. Start with the bits. So a bit is really just a Boolean value. It's true or false. It's 1 or 0, high or low. You can see all those different variations inside this one little screenshot. And then we have an asynchronous bit. It actually should be async bit. So an A bit or an asynchronous bit is a bit that can receive and send values from its own state. So, or for its own state. So you see it actually contains, I call it a behavior, but it's basically just, usually this is just its normal, where it contains a bit. And this is a bit that it is. And this is actually just the initial value. Because because what happens when an asynchronous bit receives a signal that it wants to be changed is it just forwards that signal on to whoever is listening to it. So it doesn't even actually update the internal state because it doesn't need an internal state because it's always listening for new values, and then you just forward those on. It's like a router kind of, or it's like a it's like a wire, you know, like you can connect a wire onto a bunch of different points, or you can, like, you know, it's like a bus kind of, you know, like an electronic bus. Something goes along the bus, and then everything that is on the bus that's watching that bus will see it, and it will see whatever was most recently on the bus. So for that purpose, I'm using a watch type channel. I'm using 2 of them per bit. One is to for input, and one is for output per bit. So they call them the set and the get. So I actually almost get rid of that because I'm not using that anymore. But you can see that we have a few different behaviors for bits. We can have a normal bit that just behaves like a regular signal, and we can have a clock that alternates, and then bit that's always high, bit that's always low. And then yeah, so what was I gonna say? Yeah, so you can see here that when we spawn a bit normally, you see it's spawned into its own asynchronous task in the Tokyo runtime that I've created. And all it does is it just grabs whatever it most recently knew its state was, whatever's most recently set to, and then forwards that off into whoever's listening to this bit. And then we throttle a little bit by waiting an interval, which is currently, I believe, 5 milliseconds. Yeah, 5 milliseconds. And then we voluntarily yield to the Tokyo runtime so we can execute other bits, right? Otherwise, we're just going to loop infinitely, and that's no good. So, and then in the ops, these are really gates. In fact, I just recently renamed them to gates. But the gates themselves, they can have a few different types. So you have identity, which is just that buffer that I talked about, that I showed you on the Wikipedia page, or a not gate. And then we have a binary gate, which I told you about. That is we do an and or XOR action, or we can do one that's always A. This is useful for just kind of making a binary gate act like a pass-through. Because of the way that's set up, I'm using a graph data structure in order to store all these circuits. In fact, I can show you what that actually looks like. Let's pull up the graph viz preview. Yeah, so this is actually the graph of what this circuit looks like. This circuit is translated into something like this. So you can see that the ones that are always high and low are not currently being used. But you can see that the clock is connected to some AND gates and to some, the J input is connected to some AND gates, and we have some knots for the connections, and it kind of follows the same flow that it did in the side of the script, the PALS script. By the way, this project is called PALS. It stands for Parallel Asynchronous Logic Simulator. So should have said that at the start. Sorry. But yeah. Anyway, so the gates, they go and they kind of do similar thing to the bits, where instead of just forwarding on whatever they receive as input, they first do some kind of operation, binary operation or unary operation on the bits. So you can see, yeah, so the ops or the gates, they yeah, so it just does an operation on whatever it sees. which is either and or XOR. Then unary gates do something similar. Circuits are the translation of each of these circuits, and they use a graph data structure, a directed graph from the pet graph crate, which I've going to become quite fond of. Excuse me. And it's able to parse this script, which the parser is also using nom, just like I use for assembly language, nom crate. And it's able to connect these all up into graph data structure, and it's kind of really complicated that I don't want to go into right now, but it does a depth first search to actually connect all the gates after building the graph in the parsing stage. And then I've started working on my own asynchronous runtime, just for purposes of the project. I'm not actually using it right now, but maybe I'll go over that if I end up actually using it. Then we have the main, which is just sets up a dialysis window and runs the interface. So that's about it for this project. I don't really have much more to talk about other than what I've been doing with it. I would like to eventually run a small, maybe like an 8-bit adder or some kind of ALU arithmetic unit running in this thing. That would be really cool to have. Maybe some kind of really simple computer with a program counter and instruction register and all that. But that'd be cool to have with this project. I would like to get there eventually. But for now, that's all I got. Thank you all for watching. I appreciate you all very much. If you have any questions, leave a comment. If you have any comments, leave them a comment. And I will see you next time. Hit like and subscribe, please. Peace out.